So I think we can officially start. So hello everyone, welcome to the next meetup organized jointly by quantum computing groups from Washington, Toronto and Warsaw. My name is Paweł Gora, and together with Sebastian Zając we'll be the facilitators of this meetup. And today we have pleasure to host a great speaker, Professor Burd from Drew University, and he will give a lecture titled Solving Unsolvable Problems, Taming Infinity with Quantum Measurements. So before we start, just a few announcements. As usually, this meetup is recorded, so hopefully the video will be later available on our YouTube channel. And if you have any questions during the meetup, please post your questions on our chat. If there are some urgent questions, maybe we can try to interrupt. So Professor Barry, how do you think? Would you like this meetup to be more interactive? So
absolutely. Yes.
Okay, great.
Yes.
Yes. So if there are some important urgent questions related to the slides, we will try to ask the questions during the lecture. We'll try to interrupt. But
if there are unurgent questions, please interrupt. I really like this to be a conversation.
Okay, great. So at the end there will be also a Q&A session. So if you have some more general questions not strictly related to the presentation, maybe we can also wait for Q&A, but it's up to you. And what else? So we would also like to announce our next meetings on July 9th. There will be a meetup with our guests Yuval Boger and Eric Garcel about optimizing hardware-aware solutions to quantum problems, why they're important and how to create them. In August, there will be a lecture given by Shadab Hussain and Abhinandan Pal. So in fact, Abhinandan will be the speaker. Shadab and Sebastian will be the facilitators, and Abhinandan will give a talk about Quivi, a quantum programming language. And finally, we would like to thank our partners, our sponsors for supporting this meetup. Thanks to Quantum AI Foundation, Association Quantum, Orion XNet, ArtistaQB.net, QPoland, Cambridge Quantum, and Quantum Computing India. And that's all from my side. So I will stop sharing the slides now. And Professor Barry, if you are ready, the Zoom is yours. We can start. So thank you once again for accepting our invitation. We are happy that you will give this lecture today.
And thank you again for having me. My first question is, can you read my slide?
Yes, I can read your slide. I can.
Yes.
It's large enough? Okay, at any time, if it isn't large enough, somebody just yell to me and I can enlarge it on the screen and small myself.
Okay.
So, and then again, a reminder, jump in anytime. I really like discussions rather than lectures. So, you know, just, I hardly look at the chat. Just unmute yourself and yell to me. Okay, the first note that I want to make is the following. And there we go. Oop. Okay. This talk isn't about quantum computing as we know it today. This talk came about, I think, basically, George is here. George was giving a talk in front of, I believe, this group, and I mentioned a result that had been developed in 2015 about unsolvability and undecidability, and I guess that sparked some interest in the group. So I was asked to give this talk. And honestly, this is the material that actually triggered my deep interest in quantum computing. And it's not exactly quantum computing related. It's sort of maybe not quite the next step in quantum computing. It's 10 steps from now in quantum computing. It's quantum related, but it's nothing like the gate model or the quantum annealing model that you've known and loved so far. but it's material that I love talking about. So I've done college classes on this. I'm really excited about it. So let's go here. Everyone's seen this paradox? Yes, yes, yes. Are you familiar with this?
Yes, I heard about this.
Okay. And of course, the paradox is after this, you ask, does the barber shave himself? And the answer is, if he doesn't, then he does. And if he does, then he doesn't. So what you end up with here is an assertion that causes in and of itself a contradiction, something that can never be true. And it's achieved with a trick. And that trick is self-reference coupled with a negation. So what you've got here is barber shaving the men in town who do not shave themselves. You've got the not there. And then you ask if the barber shaves himself, a self-reference. And when you combine those two tricks into one statement, you can easily generate a paradox. Now, in 1900, David Hilbert gave a now famous lecture in which he proposed problems for the next century. One of the problems was to formalize mathematics so that everything could be proved mechanically. Everything that was true could be proved mechanically. And it kind of turned out, Kurt Gödel in 1935, I believe, or was it 1931? Close enough, in the 1930s, proved that no such program is possible. And he did it with this kind of a paradox. You know, he said a statement, he said, let's issue a statement that essentially says, I as a statement am not provable. Well, if it's provable, then it's false. That shouldn't be. If it's not provable, then it's true, but it's not provable. So he generated that kind of a contradiction. And then later on, maybe 1935, Alan Turing proposed an argument that essentially said that some problems, some extremely well-defined problems, not vague problems, real mathematical problems, cannot be solved using computers. And computers hadn't been invented yet. So this was kind of an interesting theory. So let's take a look at that. I'm going to prove to you that there are problems that can't be solved. And I'm going to do it with, I have so much trouble pointing. With that, with whatever you see on the screen there.
No question.
Sure.
Is this an exercise in logic and twisted logic?
In what?
Logic
Yeah.
and twisted logic.
Well, it's certainly an exercise in logic. And whether it's twisted or not is up to you.
Man, did even talk? Send me the tester.
Hello?
Yeah, thanks for the answer, but there was an interruption.
What?
I say thank you for the answer.
I mean, it's an exercise in logic. It's valid logic. Whether you want to call it twisted or not is up to you. There's certainly a knot that's tied in this logic that will be tied in this logic. But when I call it twisted logic, that doesn't mean that it's invalid. It will be valid logic.
No, what I mean is that there is implicit trick in what I call twisted logic. Namely, if you lead me to contradictions or to self-negating statement, I am losing the linear, straightforward, step-by-step, moving to a positive result.
Okay, I see what you're saying. So let's go back for a second. I'm going to move back to the previous slide. A barber shaves all and only the men in town who don't shave themselves. Does the barber shave himself? This is a genuine example of a paradox. It is a statement that shows that logic can get us in trouble. And to resolve paradoxes like this, philosophers and logicians have been working overtime for decades. So this is, I think, what you would genuinely call twisted logic. This,
Yes,
what comes next, Turing's proof, is simply an argument that is only a paradox if you assume that every rigorous problem can be solved by computation. So what it ends up doing is using the same twist, the same turn, the same negation and self-reference in order to contradict the original assumption that every problem can be solved. So it has the same structure as one of those paradoxical statements, but it's not a paradox. It's really a contradiction of an assumption that every problem can be solved. Okay? Itamar, are you okay with that?
Itamar is now muted. Itamar, could you please confirm if it answers your question, or you maybe have some follow-up
and
questions?
I still have some quibble with it.
Okay.
And this is when you mention Gödel,
Yeah.
he is also known to program that writes programs.
Right.
Now, this discussion may be related to the puzzle that a program can write programs.
Well, programs can write programs and they can compile programs. And so a program can act on a program. And that's an essential part of this argument. I think what I'd like to do, and I do not want to discourage discussion, I just want to propose that we take your objection and move it to a Q&A period at the end of the meeting.
Wonderful, thank you.
Okay, all right. So I'm going to give some notation here. The notation is a program, parentheses, input as the parameter, stands for the run of a particular program when it's given a particular input. You've probably been reading that over and over again for the last 5 minutes, so there's no reason for me to elaborate on it. What comes next? Can the following program exist? So this is a program, I call it an algorithm, it's the same idea. A program called eventually halts. It outputs true or false, and it takes two parameters. It takes a program and an input to that program. And it says, yes, true, if after examining the program and its input, it decides that the program eventually does stop running with this input. Otherwise, if it decides that the program never stops running with that input, it outputs false. And this is called the halting problem. Does a program with a particular input halt? Now, let me just check. I'm always in danger.
I just have a question and maybe some remarks. Can I?
Yeah, sure.
Yeah, because if you show that you run program, it depends how you define, how you choose the machine which.
Oh, absolutely, absolutely.
Yes, and it doesn't mean that you assume kinds of logic in this way. And the second question, maybe more remarks, is that in physics we have also a lot of paradox. But it doesn't mean that something is wrong, but the wrong is thinking about the paradox, because we try see some kinds of things like in physics, like in general relativity, or even in quantum mechanics, that something is wrong. But of course, the wrong is not that there is a paradox, but wrong is our point of view for this paradox and our assumptions. So maybe, and the same, of course, is in the logic that that in mathematics we can describe everything by logic. As we know today, we cannot describe full mathematics by just this kind of things, and but this doesn't mean that there isn't something more than could describe it in correct way.
Okay. We have in the theory of computation an agreed upon definition of what it means to be an algorithm. And I actually will give you a glance at that later on in this talk. One of the things about that agreed upon definition of what an algorithm is, called a Turing machine, is that several other models of what it means to be an algorithm have been proposed, and every single model that's been proposed within a certain boundary agrees with what a Turing machine is. It agrees with what an algorithm is. So it's very difficult.
Excuse me, by models, what do you mean by models? Because models has a different meaning in machine learning, in mathematics, in physics.
So we have in mathematics a rigorous definition of what it means to be an algorithm and what it means to be a program. And it's not language dependent. And miraculously enough, many other proposals for what define an algorithm have come about, and they all seem to agree. They all yield exactly the same set of solutions. So if instead of defining an algorithm by virtue of Turing machines, you define it by virtue of primitive recursive functions or some other method, productions, you can prove that that all these definitions are equivalent. So in this discussion, what we've done is agreed, or we will agree, or I will agree with myself, that Turing machines is the ultimate decider of what it means to be an algorithm. And that's maybe something that we're just going to agree upon for this part of the meeting. Later on in the meeting, we'll talk about a result that came about in 2015. You can see how old I am. I still keep saying 19 when I talk about years. We'll talk about a result that came about in 2015 that proposes an alternate model that might be able to solve problems of this sort. Okay?
Yeah, okay, but if you choose Turing machine as something universal, it has also his elements, functions, and some sets, etc. So
okay, let's put that discussion to the end. I really like these challenges, and I want to hear every single one of them, and I don't want any of them to bog us down. For now, we'll discuss it as we go on. Okay. All right, so let's assume that we have an algorithm called eventually halt. It takes two inputs, a program and something that is an input to that program. And if a program with that input eventually stops running, this algorithm returns true. It's a program that examines a program with its input. Now, I think what I want to do, and I wonder if I could do this, is skip to I think, yeah, there, okay. I'm skipping slides because I'm feeling that this slide is an important one to show now. I'm going to enlarge it to make sure that you can see the whole thing. And I'll move myself. Quiet, you.
Incoming call from 508-829-3847.
That was spam. Quiet. Okay, here we go.
Incoming call from 508-829.
Quiet. All right. Yeah, for particular programs, this problem is solvable, right? If you take a look at the two programs that I've got on this slide, at a glance, you can tell whether each of them halts for a particular input or not. So for example, for the problem on the left, if you input the value, I don't know, 10, then the thing is going to print 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or maybe start with 0, I don't know, and it'll halt, it'll stop running. So an examination of that program without even trying to run it can tell you, yeah, that program stops running. And the program on the right, no, that's never going to stop running because you input a number like 10, and I guess we got to initialize count to 0. I forgot to do that, but let's put that there. So count is initialized to 0. Is 0 less than 10? Yes, so print hello. It goes back to the top of the loop. Is 0 less than 10? Yes, it is. So print hello. It goes back to the top of the loop. Is 0 less than 10? Yes, print hello. It goes on ad infinitum. So the idea here is that if by examining both of these problems, I don't have to run them. I can tell intuitively or by some formulaic method that the one on the left eventually halts and the one on the right never halts. And this is the argument that people give to say, no, you can tell whether a program halts or not. But the argument in the halting problem proof is that there's no one-size-fits-all algorithm to decide if a program halts or not. So in general, we cannot look at a program and say, this program will eventually stop running with this input. Which means he said, and I'm going to go by title back here, that I propose that this algorithm cannot possibly exist. So let's see why not. What we're going to do once again is we're going to do a self-reference, and then we're going to do a negation. And let's do that. Let's assume for a moment that this eventually halts algorithm does exist, can possibly exist. Right? Then we're going to create another algorithm that I'm going to call contrary. And it takes only one parameter. That parameter is a program. Now I'm going to give you a second to take a look at this and then tell me what you think. I'm going to make myself bigger because I like being bigger. So the contrary program does the opposite of what the eventually halts program does, but it takes a program and feeds the program itself as input. And then it does the opposite of what the eventually halts program does. Now, if this gives you a headache, I don't blame you. I mean, this is twisted in knots type logic, but it's good logic. It's real logic. So what's going on here is how does algorithm contrary work? You hand it a program. It takes that program, feeds it to itself, and then asks eventually halts, will this combination eventually halt? And if eventually halt says yes, then the contrary program runs forever. It does the opposite. And if the eventually halts program says no, this combination will run forever, then the contrary program returns true and stops. So the contrary program does the opposite of what eventually halts does. So what? I said, slides, advance. So what? There we go. if you feed the contrary program to itself, then we have a complete contradiction. If contrary fed to itself eventually stops running, then it will check with the eventually halts algorithm. It'll decide that contrary with contrary fed to itself eventually halts, and the contrary program will not stop running. So if the contrary with contrary eventually stops running, then it won't. And if contrary with contrary never stops running, then it will. So this is nonsense. This can't happen. It's the barber in town who shaves everyone who doesn't shave himself. But in this case, we don't have a genuine paradox. What we have is a contradiction to the assumption that a program called eventually halts exists. There is no such thing as an algorithm, a program that can tell for every program out there whether it eventually stops running with a particular input. And now with this, I'm going to pause for a moment and see where everyone is, because this is the bombshell that Turing discovered in 1935, and I discovered in, I don't know, undergraduate school, and it's had me thinking ever since.
So given some programs, you can construct a proof that it halts or that it doesn't, but not for every program.
Right.
Okay. I mean, this has something to do with proof, right? You're trying to prove that something halts.
It's not so much proof. So think about a compiler. What a compiler does is examines a program. A compiler is a program that examines a program and does something with it, produces some output, that output being object code or byte code or whatever you like. Now, what I want to do is create a program that always answers true or false, and its input is some other program and a proposed input to that other program.
Right.
And what I'm saying is, let's not call that program a compiler. Let's call that a super duper compiler, or what I've called here an eventually halts program. Can I write such a program? Am I able to analyze any program with any input and say, will it eventually stop running? And the answer is no.
Right.
I can analyze some programs and say, will they eventually stop running? I have methods for taking a look at this. I don't have to, look, the program on the right there, it'll never stop running. And I don't have to wait. I don't have to start running it experimentally and wait until infinity time is over to be able to tell that's never going to stop running. I can do it with my reasoning. I can, in fact, write a computer program that takes a look at that and says, come on, that's never going to stop running. Well, can I write a general program that always checks to see if any program with any input will stop running? And the answer is no, that would lead to a paradox.
I guess you can construct an algorithm eventually halts that works on some class of programs.
Absolutely. Absolutely. Now, I mean, there's another problem here that's sort of underlying the whole thing, and that is, how would you be able to tell experimentally if the program on the right ever halted? Well, you really can't. Because to be able to tell experimentally if the program on the right ever halted, you'd start running the program. And then a year later, you would say, well, it hasn't stopped running. Does that mean I can give up? And you'd say, no, because as soon as I give up, it's going to stop running. And then 100 years later, you'd look at it and it would still be running. And you'd say, okay, can I admit now that it's not going to stop running? And the answer is no, because it may take 1,000,000 years. And even after 1,000,000 years, you can't do that. So there's really no experimental way to determine.
Sorry, I miss a point here.
Yeah.
The program on the right doesn't define count.
Count is 0. I should have put
And-
that in the slide.
But it doesn't increment count.
Right.
That means that count doesn't do what count's supposed to do. Therefore, it's a wrong piece of code.
Well, right or wrong, if we
It's a misleading piece of code.
that doesn't bother me. Hey,
Well,
I have students who write misleading code all the time. The thing is, let's assume that count is 0, because I should have written it there explicitly. If not, there are some languages where it's implicitly set to 0 if you don't define it. The point is, you and I can tell that this program will never stop running. Doesn't matter whether it's a good program
it's
or not.
designed to never stop.
What?
It's designed to never stop because you don't increment the count.
Absolutely.
So what kind of do loop is there when you don't increment the index?
It's possible to write. That's all I care about. We're not talking about analyzing only good programs. We're talking about analyzing anything that can be written as a program, good or bad. Go-tos, absolutely, bring them on.
So this belongs to the class of funny programs.
In what sense are they funny?
I call it funny because nobody will accept this as acceptable code.
That's fine.
So that class is very special class. And if the logic here hinges on such class, we're very restricted.
Well,
because we try to generalize something to programs that belong to the acceptable.
well, let's take a heart monitoring program. We really don't want that to halt either. And that's a good program.
Okay.
All right?
Sorry, I withdraw. Yeah. Okay.
Yeah, okay. All right. Now
Second
let's see.
question.
Yeah. I'm sorry, go ahead.
Somebody
Yes,
raised his hand.
there is a question from Al, I guess. Yeah, you can unmute. Could you please unmute yourself because you are muted now?
Okay, I've done that. Yes, I think this may be subtly different, but maybe in your explaining this subtle difference, we'll get greater illumination on what you're demonstrating at the moment. I'm thinking of, I never know how to pronounce it, but one of you will be able to tell me, Fermat's last theorem or conjecture.
Right.
Now you could write a computer program to search for solutions to that conjecture, searching for them. And there's no way, at least there wasn't any way, that you could predict whether that program would ever stop in its search for solutions to Fermat's conjecture. Now, it turns out it's been proved that it, in more recent times, that it would never stop because it would never find any other solutions to Fermat's conjecture. He proved that with logic, and I must say, I'm not sure whether any program could be programmed to make that sort of deduction.
Okay.
Is it similar? Is it similar to the sort of problems you're postulating, or is it inherently different because there was a logical way
There was a
of
logical
actually
way, and,
proving?
without thinking too long about it, my instincts are telling me that you can take the logical way that was proved by Wiles and turn it into a program to do the checking for you. And
Yeah.
by the way, it was conjectured before Wiles's proof that there was no solution to the Fermat's last theorem problem. But Wiles showed that that wasn't the case.
Yeah.
Let's move on. I want to make sure that I don't have to say the last 10 slides in 10 seconds.
Okay.
We've got an hour, right, Helen?
Professor, there is a question regarding the halting problem on the chat, so maybe I will read it and then you will decide whether to answer it now or later.
Sure.
Will the halting problem analysis ever lead to understanding of whether or not a piece of code is productive? By productive, Ron means it's not broken.
I have to think about that one, but that gets us into the proofs of correctness and for programs. And there's a whole science surrounding that intersects with the halting problem question, but I don't know. I mean, obviously, if you want a program to halt and you can prove that it doesn't, then you've shown that it's a broken program. The other way, I'm not sure I have anything intelligent to say about it.
Okay.
All right, let's march.
Let's go on.
Yeah, let's march on. Let me see what's going on here. I just have to check my future slides to make sure that oh yeah, I just want to introduce you to this absolutely crazy thing. And I'm going to move myself over. I wish I could do that in real life, just like that. If you've studied computer science, you know that there's this complexity theory, and it says there are problems that can be solved in big O1 time, big O(n) time, big O(n) squared, big O(n) cubed. If we're willing to go to n to the 100, n to the 1 million, we call that polynomial time. There's even this thing called non-deterministic polynomial time. And essentially what that means is I'm gonna really mess up, I'm gonna really oversimplify it. What it means is that these are problems that we can't solve in polynomial time, but we can verify solutions if they're given to us in polynomial time. And these are considered very, very hard problems. But they're not the kinds of problems that I'm talking about that are unsolvable. Problems that are unsolvable, problems that are in NP are impractical to solve. They're called intractable. We just can't build computers that are going to be fast enough to solve them. And I'm going to move myself over just a little bit more because I see that my name is blocking me. I don't like that. If you're used to thinking about NP problems and intractable problems and how difficult they are to solve, they're difficult because they're extremely time consuming. But undecidable problems, unsolvable problems, the problems that I'm talking about here, that I've proved by contradiction cannot be solved. No amount of time can solve those problems. There's just no way. It just won't happen. And that's if you use the Turing's architecture. I used to tell my students that if aliens came to Earth, landed, opened their little hatch, walked out and said, we can solve the halting problem with a computer program, then we should consider them as hostile aliens because they're lying. Now, that's what I used to say to my students, but I have some other news to tell you about today. Even more amazing than the fact that there are undecidable problems is we have this terminology in the theory of computation called an oracle, and it's different from an oracle in quantum computing. In the theory of computation, an oracle is some agent that can, with no reason given whatsoever, answer an unsolvable problem for us. So what you postulate is that you're in the middle of a computation. You run into, during that computation, a problem that can't be solved. Does this program eventually halt with this input? And you consult an oracle, and the oracle magically gives you the answer, and then you keep computing on after that. Now, again, I don't like to use the terminology oracle because it gets confusing with people in quantum computing. But the point is, imagine I dream of Jeannie. Jeannie comes and you ask her, does this problem eventually halt with this input? And she goes like this. And she says no. And then you keep on trying to solve whatever other problem you're trying to solve. Turns out that if you add that to the soup of computation, then you can redo the argument about contradictions and come up with another problem that's even more difficult to solve than the traditionally unsolvable problems. And you get a whole infinite hierarchy of unsolvability. Any genie that you create who can solve one of these problems for you, you can redo the paradoxical argument and come up with an even more unsolvable problem. And so what fascinated me about as a graduate student was we have, what's the structure of this hierarchy of unsolvable problems? Enough said about that. It's you can go like this and not hear it, and you'll be fine with the rest of this talk. Okay. Now, not all unsolvable problems are crazy ones. Here's Post's correspondence problem. And Post's correspondence problem is, can I line up these dominoes with possible repetitions so that the text on the top is the same as the text on the bottom? And I'm going to skip quickly to the answer. It is yes. Helen, I assume that we have to stop after an hour? Or,
You can continue.
Yes.
Oh.
Yeah, we can. Mhm.
yes, we should?
Yes, we should. You can continue
yes.
until the end.
Okay, all right. So the answer for this particular problem is yes. It turns out that in general, this problem is unsolvable. And Emil Post proved that. And there's even a better answer. There's no way to line up these dominoes. Post's correspondence problem isn't solvable. There's even a better one, the airline pricing problem. The airline pricing problem has been shown to be undecidable. Find the lowest fare given the fare rules that airlines use to set their prices. Low fares have rules such as 2 weeks. Oh, you can read the bullets. A problem as practical as airline pricing has been shown to be undecidable. You cannot write a computer program to solve it. And this doesn't have any extensible features of negation and contradiction. So we have real problems that can't be solved, real life problems that we know there's no algorithm to solve them. Well, okay.
Amir, can you unmute and ask a question?
Sure.
Yeah. Barry, quick question on that one.
Yeah.
If you go back this slide, assuming finite, like this problem is finite or has a finite amount of input, I guess I'm lacking the intuition around how this is undecidable.
Well, the programs that I showed earlier, I guess they both had finite amount of inputs, those two little problems. But the input to a program has to be finite. That's one of the rules. So I'm gonna go back. Right? The program on the right eventually halts. Oh, no. Excuse me, I have to reset. I'm beginning to get loose. I'm beginning to worry about time. Let me march on, if you don't mind. Because how hard is the stop? Like, do I turn into a pumpkin at 2? I should march on.
Yes, we can go on. Mhm.
Okay.
We can go back to this question at the end.
Sure. Now, how do you learn to block karate punches? Has anybody seen The Karate Kid? Well, it actually turns out to be in the write-up for this talk. Embedded within the car-waxing problem is the same structure as the punch blocking problem. So if you want to learn how to block karate punches in the movie Karate Kid, you don't practice blocking karate punches. Instead, you practice waxing cars, wax on, wax off. So that's taking a problem and reducing it to a different problem. So here's the notion of reducibility. And this is one that my students find puzzling. I hope that you can ascertain what's going on here. I'm going to let you read it instead of my talking through it. I think that's better, more effective. Reducing one problem to another means that you show that if you can solve the other problem, then you can turn it into a solution to the original problem. So if I can figure out how to practice wax on, wax off, then I can use the solution to the wax on, wax off problem to solve the punch blocking problem. And that's the way that Emil Post demonstrated the Post correspondence problem was unsolvable, because he showed that if you can solve Post correspondence problem, you can solve the halting problem, but you can't solve the halting problem. Now, reducibility is an important concept. Oh, here's another example. How can you show that two shoestrings are knotted in the same way? I know absolutely nothing about knot theory. I copied this from one or two unnamed sources. A quandle is a set with, you can reduce it to some sort of algebraic structure. Don't ask, I don't know. It's just, you take a problem that's about shoestrings and you turn it into another problem, solve the other problem, and it gives you an answer about shoestrings. So that's reducibility. And this is what is an algorithm. Turing machines. Again, I'm going to move on because we've had such a stimulating discussion, which I like, that I just must press onward. The spectral gap. And this is the point where there's a drum roll. In 2015, Wyatt, I didn't expect 2 spam phone
Incoming
calls.
call from 516.
Yeah, and that's the neighbor. That's an important call, but I'm going to have to answer it later. The spectral gap in 2015, some researchers proved that the spectral gap problem in physics is unsolvable, undecidable. So what does a spectral gap mean? Spectral gap means you measure the difference between the ground state of a system, the lowest state that the system can have, and the first excited state, the next state that the system has. So you want to measure the difference in energies between an electron being up here and an electron being here. And this is a helium atom, enlarged and not to scale. But now, how do you find out what the difference between the energy of this electron is and the energy of that electron is?
Shine
Well,
light on it.
what?
Shine light on it.
Yeah. What? Shine light on it. And when I'm saying this, I'm realizing that I was trying to point and you didn't see my pointer. Or did you? No. Okay. All right. How do you find the difference in the two energies? And the answer, and now it's time for Pixar's quality animation. You let one of the electrons go back to its ground state. That emits a photon. You put the photon through a prism of something, and you measure the spectral qualities here. So that's how you do it. And don't ask me too much about that because I'll have to make up answers. Anyway, there are many examples of spectral gap problems. What's the difference between the ground state and the first excited state? Here's another example. If you have a two-dimensional lattice of things like electrons, some of which are spin up and the others are spin down, you can start them in one state, and they're going to end up in another state. They're going to interact with one another and find a place of equilibrium in a ground state. What's the difference between the ground state and the first excited state? There are all kinds of examples of spectral gap questions. And for a long time, physicists have tried to figure out how to calculate this in general. And the result in 2015 was that, in general, the spectral gap problem is undecidable. We can experimentally measure it, but we can't solve the problem for every case. There is just no general solution to this problem. Oh boy, what does that mean? I have 3 minutes to tell you. What if we can reduce the airline pricing problem to a spectral gap problem? What if we can go from wax on, wax off to karate punch blocking? What if we can go from airline price to spectral gap? What if we can find a structural problem, a physics problem, in which the spectral gap problem is similar to the halting problem or the airline pricing problem? Then what we can do is take our unsolvable problem, reduce it to a spectral gap problem, and then measure the spectral gap in order to find a solution. And if I'm not mistaken, I have a slide that says that. Ah, yes. I'm going to jump ahead. Here it is. Take a problem that we know is unsolvable in the Turing architecture or in the von Neumann architecture of our machines today. Rename the parts of it so that it has the names of a spectral gap problem with the same structure. Then measure the spectral gap by having an electron fall or by having other electrons change their upsies and downies, and then take the answer to that and work it back into a solution to the unsolvable problem, the problem that was immediately unsolvable. Now, that's not quantum computing as we know it today. There's something quantum about it, but it's, what, 10 generations forward? I don't know. If it can be done, that's the program. That's what I find so exciting about this result from 2015. Unsolvable programs can be solved. If aliens come from another planet and say, we can solve the halting problem, maybe we should lend them an ear. I give it to you. That's my talk. That's my spiel. Thank you.
Okay, thank you, Professor. Very interesting talk, and we have some also interesting discussions on our chat. So there were questions regarding this post-correspondence problem, and also there was a question regarding the domino problem. How is the dominoes problem unsolvable? So there was.
So let me ask.
Yes.
Let me ask a procedural question. How much time do we have for questions?
As far as I know, we don't have a specific limit. Helen, is this correct?
True.
Okay.
Yeah.
Let me go back to the slide about post-correspondence problem. So, I mean, here's a situation. Come on. Is that going to happen? Maybe not. I just have to find. There it is. Okay. So, I mean, in this case, you have these post-correspondence problem is the dominoes problem. You have these dominoes and you line them up on the top and you line them up on the bottom. They're the same dominoes, but with repetitions. And you find that if you're restricted to that set of dominoes, the ones on the top, then you can line them up in a way such that the text on the top is the same as the text on the bottom. For the bottom line of dominoes, A, B, C, A, B, C, on the top row and on the bottom row, A, B, C, A, B, C, the same sequence of characters. And that would be impossible. Such an alignment would be impossible if you started with this set of dominoes, because no matter how you repeat dominoes and put them in a sequence, there's no way in hell that the number of letters on the top isn't going to be more than the number of letters on the bottom. So you can't have, as it is in this, what I'm going to turn this into pointer options, laser pointer. Ah, yes, now you can see this. Yeah, we start with these 4 dominoes, we line them up this way. We have that this sequence of letters is in the same order as this sequence of letters. Let's see what happens now if I do this. Well, for some reason. Okay, there's no way to line up those dominoes so that that's going to happen, because no matter how you line them up, the number of letters on top is going to be more than the number of letters on the bottom. Now, what Post did was he showed that we can take the halting problem and rephrase it into a dominoes problem. So he showed that we can, instead of dominoes with letters A, B, C on top, dominoes with letters corresponding to features of the halting problem, and that lining up dominoes so that the top row was the same as the bottom row could be mimicked to have the same structure as a solution to the halting problem. He did a reduction. And thus he proved that if you can solve the halting problem, if you can solve post-correspondence problem with dominoes, you can take that solution and turn it into a solution to the halting problem. So you can't solve post-correspondence problem. Does that answer the question?
I hope it does.
Whoever asked it,
Yes. So yeah, it was asked by Santanu. So Santanu, I hope that it answers your question. But if you have any doubts, feel free to just follow up. And there are some new questions. The first one
Yeah.
is from Bettina.
Oh.
hello, Bettina.
Yes, and could you tell how the spectral problem is defined as a computational problem, not as a physical experiment?
Not a physicist.
Okay.
I mean, I can tell you that, you know, physicists do what they do. They take problems of any sort, turn them into some kind of calculation and try to solve the equations.
Mm-hmm.
And what the researchers in 2015 showed was that in general, if you can solve the halting problem, if you can solve those equations in general for spectral gap problems, then you can solve the halting problem. And by the way, they did it by drawing a correspondence between the spectral gap problem and what they defined as a quantum Turing machine. But now I'm throwing more information into the mix. Bettina, did that answer your question?
Yeah, thank you. It's the computational formulation is that the equations describing the physical systems are given, and then one has to decide whether there is a spectral gap or not.
Right, and there are certain computations that just can't be done.
Yeah, thank you.
Just as you can't square a circle or trisect.
Mm-hmm.
Not possible. Solve a
Okay,
physical
good.
equation.
Yeah, there was another question from Ron. Can we categorize the airline problem as a graph problem, or are graphs just a tool?
You can certainly try to categorize it as a graph problem. Oh man, sorry about this.
Incoming call from 973-377-5183 for Barry Burd.
Quiet. Wouldn't you know it? Before this talk, quiet, Hamlin. Before this talk, I said to myself, I don't need to silence my phones. Nobody's going to call me. Yeah, I mean, I think I don't know the details, but I think part of it is certainly a graph problem. It's got to be, right? You're talking about connecting from Philadelphia to Pittsburgh and from Pittsburgh to Chicago. There have to be some aspects of it that are graph-like. I was standing in the room, by the way, when the four-color theorem result was announced. It was in the mailroom at the University of Illinois. I was standing there.
Great.
A tidbit.
All right.
May I ask a question?
Sure.
Sure.
The self-reference seems to me connected to some recursion. Am I wrong?
Well, you're not wrong at all. Oh my God.
Incoming
Anna,
call from
stop it.
973-377.
Sorry. I keep thinking that that's the last call I'm going to receive, and it just doesn't happen. The first definition of, let's call it, solvability was in Gödel's paper, where he proved that there were undecidable questions in mathematics. And there he used something called primitive recursive functions. And so the idea there was to define computation by building it up from only a certain set of operations. One of them was recursion. And primitive recursion, in fact, was bounded recursion, recursion in which you have to stop. And then there's another that's full recursion, recursion in which you don't have to stop. So there's a connection there. It turns out that primitive recursive functions are structurally identical to Turing machines.
Wonderful. So how about induction?
Yeah, induction is
As a tool of proving things.
Yeah, I mean, induction is basically a form of recursion.
Right.
We just don't normally think of it that way.
Yes, yes. Thank you.
Other questions, please. I love talking about
Yes, yes. There are some other questions. There's a question from Tamas. Tamas Varga, do we need?
I just have to say, if you have a
Yes,
question, please don't call me on my phone. We got too much of that. Okay, yes.
Okay. Do we need an infinite precision measurements to physically solve the spectral gap problem? So Tamas is wondering about the practicality of the physical solution in the general case.
Yeah, that is an issue. That's definitely an issue.
Mhm.
You would need infinite precision measurements.
Okay, good.
Nothing we can do about that. I guess when I wake up in the middle of the night, I'll have an argument to say, well, we shouldn't worry about that. And I'll write it down on a piece of paper. It is an issue.
All right, good.
I guess
Okay.
it's a serious issue in the case of a problem that involves chaos. It is not a serious issue in a problem that doesn't involve chaos, because then we can just get ourselves to enough precision and solve the problem that way. But you're right, there is something to talk about there.
All right. Let's see if we have more questions.
Yes,
Okay,
there is about the title.
Yes, go on.
Now that we mention infinity, what the role of the infinity that mentioned in your title to the talk? Like, how can you use, I mean, yeah, I try to make sense of this infinity that is in the title of the talk.
I confess that I have to remember what the title of my talk is, but let me take a
Okay,
look.
somebody can read it.
Taming infinity, right. Infinity is when a program runs forever, or is destined to run forever.
Oh, so that's halting.
Yeah.
Okay.
All right. Do we have more questions?
How about repeating the measurements so many times and taking average to overcome difficulty?
What difficulty are we talking about?
Well, the talk is laced with many difficulties
I'm
because
going
it's
to
very hot in
Incoming call from
Toronto.
wait a minute, 1 sec. I've just got to
Okay.
stop. I don't know what to do about this. I'm sorry, go ahead.
This is a hot day in Toronto. I'm sweating. It's no air condition. And the talk raises many, many issues, and that my head is a bit, swinging at this
Okay.
point. So I know that Monte Carlo method overcomes many, many computational difficulties by repeating the same thing and taking average.
Right.
Repeating the trajectories, computing many, many trajectories that we don't know if they are relevant or not, but somehow the average magically fits. So maybe some of the difficulties that I find in the talk may be solved by Monte Carlo approach.
Well, it's conceivable that it's certainly true that the Monte Carlo approach can make headway towards certain problems that are unsolvable. But let's think for a moment about the problem of whether a program with a certain input eventually halts or not. An average answer to that question could potentially tell us absolutely nothing.
Oh,
And I'll give you an example.
lovely.
Well, let's say that program A with input I is destined to halt after 1,000,000 years. How many trials would it take us to discover that? How would we, every trial that we would do would tell us that it doesn't halt, that it never halts. So the average of all those trials would be, no, this program never stops running. And yet, if we were willing to wait 1,000,000 years, I know I'm willing, I'd like to live forever, we would get the opposite answer, the completely opposite answer.
Cool. Thank you.
I'm proud of myself. I can answer some of these questions.
Mhm.
That's nice.
Yeah.
Okay. So there's another question from Tamas. What if we had perfect qubits, as many as we wish? Would it suffice to solve the spectral gap problem?
The theory is that quantum computing can't even solve NP problems more efficiently than, I don't know the exact details of this, but NP complete problems are easier to solve than unsolvable problems. And as far as all the conjectures are going right now, quantum computing as we know it, at least the gate model, can't help us with NP complete problems. So that bodes poorly for them helping us to solve unsolvable problems. Now, it also, I mean, it depends on what you call quantum computing. I think someday we might call measuring the spectral gap an aspect of quantum computing. It's a very different model for quantum computing, but hey, you know, it's down there in the microscopic realm, subatomic realm.
Okay. There is a question from Al, who has raised his hand. So yeah, please, Al.
Hi there. I've remembered to switch on my microphone this time. Yeah, I was just thinking of some examples, maybe like the traveling salesman problem, which I gather is non-deterministic. You can't work out the optimum tour a traveling salesman can do to a number of cities without repeating a city. But there are heuristic ways of doing it using Monte Carlo type methods where you can improve on routes by keep on trying different approaches, but you can't possibly try all. Combinatorially infeasible to explore all possible routes for a big tour problem. So that's, I can't remember the various classifications for problems, but that's a problem that, yes, you can solve in a way, but you can never be sure that you've got the best answer. And I would think that chess falls into that sort of category as well. And then I wonder whether the sort of methods that you're considering with the next generation of quantum computing has some parallel with things in the way that, for instance, other physical phenomena can solve problems, like bubbles over various frameworks can find the best way of spanning them. And it is otherwise a very computationally difficult problem.
I'm not sure I know how to distill that into a question, or maybe is it a comment?
It's more a comment than a question, which could be filled in perhaps to say if there are what you would know what linkages there are to the sort of work you're doing and to those sort of problems, which I remember seeing on TV and also in my past learning, some of these things being thrown up as examples of computationally difficult problems.
Let me dispel a myth that I think you mentioned in what you just said. I am not working on this problem. I am not a researcher of this problem. I don't have anything to contribute to the spectral gap problem or the theory of computation. I've written a couple of papers in the theory of computation, but I'm far from what you'd call a researcher. I consider myself a journalist in this field. I'm reporting on it. I'm reporting on it for a more selective audience than the general public here. In terms of the question that I believe you're posing, again, the kinds of problems that we're talking about in this discussion, and I'm going to go back to my, come on, there it is. Kinds of questions that we're posing in this discussion are more difficult than the traveling salesman problem. Whoa, here we go. Come on, there it is. The traveling salesman problem belongs here. It's solvable. It's just not practical to solve. It's called intractable. Yeah. I mean, you know, even if you got yourself more powerful hardware, the size of the problem, the amount of time it takes to solve the problem would grow too fast with increasing input. So you'd never be able to catch up with it, no matter how many times you went to Best Buy and got more memory. That's not the kind of problem I'm talking about here. I'm talking about this kind. The ones where, for one reason or another, there's known to be absolutely no solution. And I guess my brain is tuned toward those problems. When somebody says, can we find an approximate solution to certain problems? Yes, we can, but Barry loves these paradoxical, absolutely can't do impossible things. And one of the things I like about it is because I'm kind of a fan of self-reference. I find it to be a fascinating thing. Uncountability of the real numbers. There's just, you know, a whole theory built around this. But also, I'm fascinated by the question of how can you prove that something cannot be done? I mean, is it difficult or is it impossible? If it's impossible, how do you know that it's impossible? How can you say something definite about something that's phrased in such a negative way? So when I discuss this with my students and I hand them an example of a problem and I ask, can it eventually be solved or not? Is it a solvable problem? One of their knee-jerk reactions is to say, no, it's not solvable because you'd have to wait too long.
Yeah.
And that's not really a proof. That's evidence. The real proof comes when you do one of these self-contradiction proofs or when you reduce one problem to another. And that's kind of what fascinates me. Are there approximate solutions to a lot of these problems? Absolutely. But that's not where my head is at. So as much as I appreciate the practicality of approximate solutions, I'm this pie in the sky guy who loves to talk about, is it possible at all? And if it's not possible, how would we ever know?
Yeah. Actually, well, stop me if there's somebody else that wants to come in, by the way. I've got a very trivial, in some ways, maths challenge that arose from a group of people that play at mathematics. And if you like, I can describe that, and maybe some of you would enjoy it. And part of it, it is difficult to prove, and maybe impossible to prove, whether there is any higher solution. In some parallels to Fermat's last theorem, where actually it was eventually proved that there are no higher solutions, and that may be the case with this, but at the moment I don't know, and I haven't got a proof.
Okay.
It's a really trivial problem that arose from an even more trivial problem. Would you like me to describe it?
Well, we've got a hand up here from Ron.
Yeah.
Let's-
Okay. So I'll hang on, and then if you want to come back to
Okay.
this.
I'm just curious, does it involve powers of
Yeah.
numbers and sums?
It's to do with building a long string of numbers and finding a particular type of arrangement of those numbers.
Okay, that's different than what I'm thinking. Ron, what's
Hey, Barry.
Yeah.
This is Ron Schreiner. And
By
a
the way,
question.
you're right. You're right on with all your critiques of my.
I appreciate, I really enjoy being of some help there. I had a quick question about your correspondence problem and the dominoes that you selected.
Right.
When that slide pops up, it's immediately obvious to me, just visually looking at it, there's no solution to it. Did you choose that set of dominoes for a particular reason, or?
So let's go back to that.
And then I mean, it's conceivable you could have had a set of dominoes where it wasn't obvious at all.
Yeah.
So does that imply that, or is there a challenge there to be able to write a program to decide whether it's solvable or not?
Yeah. So, I mean, look, we've got these two programs, and at a glance, I'm going to move out of the way. Come on, here we go. We've got these two programs, and at a glance, you can tell that one of them eventually halts and the other one never halts. And for particular programs, you can tell that.
Right.
Now,
and then if you decompile that or take it back to the correspondence problem, is the challenge to write a program that could make that decision for the correspondence problem?
I can write a program that makes a decision for both of these.
Okay.
I can definitely algorithmically tell you that the one on the left will eventually halt and the one on the right will never halt. And I can do that without running them. I can just look at them. I can write a computer program that can analyze them and say, yeah, duh. That's what the program will end up repeating. Duh. This program on the right never holds. Now, you know, can I line up these dominoes? Well, it's not obvious, but it turns out that I can. Can I line up these dominoes? Well, it's pretty obvious at a glance that you can't line them up.
Exactly. Yeah. Okay.
So the question is, can I solve the problem in general? If I give you a bunch of dominoes, do you have a surefire way?
This would not be a generic solution to the halting problem or to this type of problem. This would be a specific solution to this exact problem. If you were to write a program to decide whether this set of dominoes is solvable or not. That would be a
Yeah.
specific one. It's not a generic one. Okay.
Yeah.
All right. Okay.
In general, if I try to write a program that solves this problem for every possible set of dominoes, I will fail.
Gotcha. Okay. Thanks.
Okay, thank you. Thanks, Ron. So in the meanwhile, there was a question from Mary. I'm not sure if it has been answered. Are there different types of recursion? So I think that there was a discussion about recursions, and probably that was the question related to this discussion. Maybe Mary, if Mary is still with us, maybe she can clarify the question. Yeah, there's already the answer from Ron that yes, there are lots of types of recursion, of course.
Yeah, I mean, I guess it depends on what you consider different types.
Okay, so maybe you can elaborate a bit on this if you are interested, of course. I'm not sure if Mary is still with us. Let me check. Yes, it looks that Mary is still here, so maybe she can unmute herself to ask. If not, then maybe there are some other questions now.
Hi, Barry. This is Deb.
Hey, Deb, how are you doing?
I'm doing okay.
Did you get
Hey,
my latest? Did you
you
get my
mentioned
latest email?
Yeah.
Okay.
You mentioned about quantum oracle and the classical oracle. Can you throw some light on this?
They're really not related. I suspect that the terminology quantum oracle has its roots somehow in the terminology as it relates to the theory of computation. But a quantum oracle, that's what a quantum oracle is. I won't go over that in a meeting of quantum computing meetup. A classical oracle, think of it as a completely different thing. It's simply an agent that we hypothesize can solve an unsolvable problem. And how it does it, it's just a black box. So if I imagine that I have the ability in the middle of a computation to ask someone, will this program with this input eventually halt? And get back an answer. Then the question is, can I use that answer to solve other problems? And I can solve some other problems, but I can't solve all other problems. There are problems that are even more difficult than the halting problem. So I mean, I think if you're searching for a different kind of oracle than the one that you know from quantum computing, that's not what this is about. This is about, let's call it a genie instead of an oracle. The name in theory of computation should be genie. It's just someone who, an all-knowing something or other that can, for some reason, answer a question that's otherwise unsolvable. And how does the theory progress after you have that answer? Deb, does that help?
No, I mean, in Grover's algorithm, we use oracle also, the quantum oracle, right? So what exactly the difference you're trying to make here?
I think there's really the difference of them being two completely different things. That I made myself, I intentionally didn't use the word oracle in my slides.
Mm-hmm.
And then I went ahead and blurted it out during my talk.
Okay.
But it's misleading to have done so.
Okay. Thank you.
Yeah.
Is this a fair question to ask about this oracle that is hypothesized to solve unsolvable problems and then build a theory using that kind or relating to this kind of relying on this oracle? What's the practicality of that kind of theory?
I mean, what's the practicality of the Mona Lisa?
Well, it inspires imagination.
There we go.
But
I'm bored. You're going to help me with this, right?
theory,
George still
theory
here?
of
It's
computing.
mathematics. It's beautiful.
Me too. But the theory of computation and computer science and so on, things are exact. They are not up to the imagination in a loose way.
I would argue against that, but
Good.
I mean,
I love this.
yeah, I mean, honestly, I find the theory of computation to be fascinating and beautiful. And as it becomes more and more abstract, it just continues to be interesting to me.
So are you using this as synonym to complexity theory?
Well, complexity, again, is a level of difficulty that's below unsolvability.
Okay.
When you talk about NP problems.
Okay.
Yeah.
I'm with you. Okay.
Yeah.
So maybe I can continue a question that was answered about the unlimited number of qubits and rephrase it differently by asking, people talk about quantum computing advantage. Now, imagine in the spirit of Oracle that I have unlimited quantum advantage, supremacy, blah, blah, blah. Suppose, will this help to deal with these problems or not?
Well, what does unlimited mean?
Namely, the technology, all the limitations that we are facing today, unstable of the gates and the circuits, and the collapse of the wave function, and so on and so forth, that quantum computing is facing as challenges now. Suppose there is a magician who can erase those and tell us, hey, use the quantum computer that I give you, and then the question is it capable of dealing with the challenges that you are introducing?
Yeah, I'm going to go back to this slide. So you're talking about, can we solve undecidable problems if we have noise-free, perfect quantum computing? And
yeah, or
the
practically
theory,
quantum chemistry.
Yeah,
that is very challenging.
Right. The conjecture right now is that if we have perfect quantum computing, we can't even do better with NP problems. Now that hasn't been proven, but it's believed by many people. It's the going opinion. So if perfect or unlimited quantum computing can't solve NP problems better than classical computers, they're not going to help with undecidable problems.
Yeah, that's the answer you gave before. Okay. Okay.
I'm glad that I've been consistent.
Yes, you are consistent, and that helps logicians.
Okay.
All right, I can see one more question on our chat. This is a question from Kushi. How can we define, quantify which problems can be solved using reducibility?
I'm not sure I know what you mean by define, quantify. The approach that's taken is, if you're handed a problem and you want to know if it's unsolvable, you try to reduce something like the halting problem to it. And if you can't do that, then you switch gears and you try to solve the problem. So it takes a lot of work to show that a problem is unsolvable, unless it's, you know, right there out in front and fairly easy to do. In most cases, when I propose this such and such a problem is unsolvable in a theory of computation class, students kind of, you know, grit their teeth, and we're going to go through a difficult proof here. You know, is it a difficult proof or not? You know, depends on who's asking. But there's, I guess the question is there a classification of unsolvable problems? And I mean, there are many ways of approaching it. I don't know if one that's more fruitful than simply reducing whatever problem you're given to, or reducing a halting problem to whatever problem you're given. Who asked the question, and did I answer it?
Yeah, it was a question from Kushi. I'm not sure if I hope that this is a good answer to this question. But Kushi, if you have any doubts, you can follow up possibly.
I don't know. I don't know of a quick way of classifying unsolvable problems.
Mm-hmm.
You just tough it out for each one, for each problem.
Okay. Okay. There was one more question on our chat regarding the traveling salesman problem, and the question is whether quantum computing would be able to solve that class of problems.
Well, yeah, the theory is no. I mean, can they solve them? Yes. Can they solve them in a reasonable amount of time? The current guess is that they can't.
Mm-hmm. Okay. But classical computers also currently cannot solve them in a reasonable time, of course. But there is a hope that maybe some heuristic algorithms might be more efficient.
Absolutely. We love heuristics when we have to get an answer to a problem, and we're not insisting on absolute truth of the answer.
Okay.
Heuristics are wonderful for that.
All right. Okay. Do we have any more questions? No.
I'm going to flip to the very last slide here and remind you that I am Barry Burd, and my email address is barry@burd.org. And anybody who has further questions or further correspondence, please feel free to get in touch with me.
Okay, great. Thank you very much, Barry. Okay, so the Q&A session took more than 40 minutes, but it was very interesting and inspiring. So thank you, Barry, for staying with us.
And thank you.
Okay, great. And thanks once again for the great presentation. And I think that's probably all. I don't see more questions on our chat, so I think we can finish for today. So Barry, thank you once again for a great presentation. I would like to thank all the participants for attending, and we hope to see all of you on our next meetups. So I think you can stop recording now, Helen. And as usually, the video will be available on our YouTube channel later. Okay, great. So I think that's all for today. Thank you. Have a good afternoon, evening, wherever you are, and have a good week ahead. And let's meet again on our next meetup, hopefully. And as Barry said, if you have any questions, feel free to contact him, to reach him out by email.